and they're going through some areas.
Whoa.
I know. I like emphasizing that, even though it's a scary integral, because you guys are still so comfortable with calculus. They're just relationships. That's what equations are. It tells you that's what it means. If you add up all the field lines going through an area, you got flux. Dot. Dot product because, remember, use this as our area. Here's my B fields. Excuse me. You're welcome. Maximum flux. Minimum flux. So the angle matters. Hence the dot product. What direction is A on this?
Towards up.
I'll buy that. It's perpendicular to the plane.
That's what you say,
Yeah,
depends
just
on
along
which
this
way the B
axis.
feels.
So-
Technically, by convention, I don't think I've mentioned this, usually it hasn't come up. If the current's going this way, then we'll say A is this way. It's like the magnetic moment. Same thing. But yeah, the area is perpendicular, the area vector is perpendicular to the plane of that surface. Right here.
So it's a dot product, so it's about the parallelness, but the area is only considered parallel because we say the direction of the area is perpendicular.
Yeah.
So on a practical level, like the B field has to be perpendicular to like the opening of the loop kind of thing. I don't know if,
So like that.
so we're saying that they're parallel, but really they're,
Yeah, that's still throw some off. So
Okay.
I'm trying to do this.
yeah.
How should I draw A?
Well,
Up or down?
One of them.
Yes.
Yeah, because,
There's the area. So yeah, it gets confusing because the area, the vector representing the area is perpendicular to the plane of the surface. But we did that with normal forces too. This always pushes perpendicularly. So in this case, A and B are in line with each other. They're parallel or anti-parallel. So 0 or 180. And the cosine of 0 or 180 is?
1.
1, thus you have maximum flux.
So you get the same answer whether A is up or down for that? Like it doesn't matter if it's anti-parallel, it doesn't change the sign of the answer?
Cosine of 0 is?
Or-
1. Cosine of 180 is? -1. So it changes the sign.
It changes the sign, okay,
But that just tells you, oh, the field lines are going this way, or the field lines are going this way.
okay.
You usually get that from the setup or the picture anyway.
So, yeah. Yeah, I like it better when we can figure it out based on logic instead of.
I always try to do that. That's why, from the get-go, I'm always like, stop and understand the question, draw a picture. That's why I try to, on the test, ask you the steps. Because if I skip the D, you might not think about A, B, or C and just be stumped. So hopefully that's easier.
Thank you.
Likewise, we're going to do, Gauss's law was E dot dA, same thing. Just electric field lines going through that surface, that Gaussian surface. Here it's an Amperian loop. So law is what in words? Has something to do with EMF. Good.
Is the
EMF?
derivative, the negative derivative of the flux?
That's a good, yes. Good right here. Flux leads to EMF, which leads to the current. So the negative, or the inverse, negative word, I guess, clear it. How the road, Doug? Get started?
Hasn't started yet. So,
don't know what that'll mean, but.
Maggie said
Some.
you can start her out.
Yeah.
So thank you, Brad. So it's negative rate of change, the derivative is, right, it's the slope of the flux. So if the flux is constant, what's the derivative of that? Zero. No EMF will be induced. If the flux is changing, you get an EMF. That's Faraday's law of words. A change in flux induces an EMF. You saw that starting last week. I mean, in here, you saw it before that, even in flipped physics. You started seeing it with motional EMF. Let's look at this one again, the generator. You got B field lines going through here. Well, what if you rotate the loop in this B field? What happens?
The flux is changing.
Right,
If
the
the
flux
area
is changing.
not the physical movement.
That was the key. That is exactly right. Go back. Oh.
So is that the generator?
Yeah, if I rotated this in this,
Uh-huh.
I'm generating electricity. Because
So-
the change in flux here induces an EMF. The EMF, that's a voltage. That makes current flow in the ring. And if I pull it out and use it, I've generated electricity that I can now use.
But your hoop has to have current flowing through it for that to be true, or no?
Yeah, generators generate electricity. But it's because you're changing the flux somehow, either by rotating or moving a conductor in a magnetic field, or varying the magnetic field around the conductor, as long as there's a change. I'll give you 3 examples, again. It's that induced EMF that gets the current flowing. Here it is. Back to motional EMF. We had like say this is all in a D field that comes out of the board, and you move this bar with V. So initially there's no current flowing in that loop or the bar. As you move it, we did the Lorentz force stuff. Brian and I were just reviewing it, sort of different, slightly different scenario. Let's walk through it as we do. V, see little charge sitting in here, charge Q, moving through the field. V, cross B out of the board. Positive charges go down. Okay. Are you guys getting that? I need more input. What are you getting? Because, you know, this is it. Yeah. Sarah, how'd you do this week? I'm glad are you feeling better?
Yes,
Were you able to talk to anybody?
yes. Yeah, thank you.
Can you do the right hand rule?
I'm rusty, but yes.
Well, that's where I go. Hold your hand up. Tell me when you don't have it.
Okay.
V is your fingers. B is out of the board, so face your palm out. B crossed into B. So the force is down on positive charges, so conventional current goes this way. The electrons, of course, go the other way.
We call that an induced current.
That's an induced current. That was just back from the magnetic force is QB cross B. We moved the conductor. That was Unit 1, Chapter 12. It became more conspicuous when bad choice of words, yeah. In Unit 16 on motional EMF, we started moving the conductor itself through these fields, but that's still moving charges. So they still feel that Lorentz force, and current starts flowing. That is one totally valid way of looking at why current starts flowing, an induced current. Before, go ahead. times acceleration, charge being accelerated, and this one, turn. So there can be a Lorentz force due to an electric field, and there can be a Lorentz force due to a magnetic field. Both of those influence charging.
Is the force exerted on a charge by a field?
Because it's moving.
Because it's moving. Thank you.
Well, the magnetic field.
Wait,
It doesn't
say
have to be
that again.
moving. The electric field can get it accelerating from rest.
Okay.
Magnetic field only influences it when it's moving.
Can you say the word first again? Is the force on?
It's the force on a charge
On,
created by an electric field or a magnetic field.
We did this initially, I
You
didn't,
call it that then. No need to muddy the waters. But now we have this additional magnetic force. You call that an electric force, this is a magnetic force. These together in terms of Lorentz force.
So it's the force on an electric charge because, that's the first part, because it's moving through an electric field.
Magnetic field.
Sorry, magnetic field.
Yep.
yeah, so electric fields
Influence charges, period. Magnetic fields do not necessarily influence charges. If they're red.
But aside from that problem, in practical, like, wouldn't there have to be both? We have two charges always, because they would either repel or attract, so then they're moving, so then that, based on that moving, then they create a new field.
So proud.
Okay.
Yes, to recognize that. If you have two charges and two positive charges, they're gonna repel. So this one feels a force because of this guy's electric field. That's that first term. Now, there's motion. Is there an external B field that they're moving through? Not initially.
they generate their own when they start moving.
But moving
right?
charges create their own B fields. Notice we got a bunch of charges moving in a wire. There's a B field around the wire. And that B field can influence neighboring charges. So yeah, once they start moving, then
So basically, the only case you wouldn't have a B field is if you had one static charge that was
right,
not near it.
right.
Okay, so the E in the equation on the Lorentz force, so I know that there was an electric field that was pointed upwards in that bar. Is that what that E is?
No, this was generic, talking about Lorentz force. That could be any electric field. I'll get back to this
Okay.
once it seems settled.
Okay.
So,
That magnetic force gets these charges moving. Now there's a current, you can see it. We're good there?
Yeah.
You can approach this a totally different way. That's how motional EMF chapter did it. Let's look at it with Faraday's law.
flux, let's look at the flux.
There's so many field lines coming out at us, right? Okay, one here, one here, one here, one here. As the bar moves that way, what happens to the flux?
Increases.
It increases, hence it's changing. A change in magnetic flux creates / induces an EMF, a motional EMF,
That's a voltage.
an electric potential. So that pushes the charges